right, welcome ladies and gentlemen. This is our video on reaction mechanisms. In this, I'm going to be talking about what a reaction mechanism is and how we can use it to determine order and rate law. So this is another method of determining order. We've talked about two so far. This is the third. A reaction mechanism is the idea that a chemical reaction might not happen in one single step as written in the overall equation. That in fact, in order to get the overall reaction, a series of what are called elementary steps have to occur. And that series of steps is what we call a reaction mechanism. I equate this to the idea of recipes in cooking. That, you know, in order to get a cake does not magically appear from the individual series of ingredients. You don't go from flour and eggs and sugar to magically getting cake. You have to do things in a certain order. And the order that you do it in cooking is called a recipe. Chemical reactions are very, very similar. The order in which the reactants collide with one another and interact with one another in order to ultimately form the products is what is called the reaction mechanism. And the series of steps, we call each individual step an elementary step. So as an example, if we consider this overall reaction, 2NO plus O2 yields 2NO2, this is the overall process, what you start with and what you end with. But upon study, it's been found that in this reaction N2O2 is detected. Now N2O2 is not a reactant, N2O2 is not a product. This is kind of like in the process of making cake. Cake batter might be detected. Cake batter is not a reactant, cake batter is not a product. It's not what you want to end up with, but it's something that was made along the way. So what's been proposed for this individual chemical reaction is that the reaction probably occurs. It's proposed. This is what we think this is our model to try to explain our results, is that the reaction might be occurring in two, what are we called, elementary steps. That first, the two NO molecules shown here, maybe they collide and maybe they make N2O2, but then that N2O2, once it's made, it then goes on to step 2 and it reacts with the oxygen. So because it's produced in the first elementary step and then used up in the second elementary step, that would account for us not seeing it accumulate over time, meaning we made it and then we almost immediately used it. But it would account for the fact that we do in fact detect it during the reaction. So this together is what we call the reaction mechanism. It's the series of elementary steps that try to explain the overall balanced equation. And if you'll notice, when we add these two steps together, note just like adding any sort of reaction together, reactants stay reactants, products stay products, but because the N2O2 is the same on both sides, it would cancel out and not be a part of the overall balanced equation. Now, reaction intermediates. This is a species that appear in the reaction mechanism, but not in the overall reaction. And an intermediate, by definition, is something that is formed early on, but then later on consumed. Formed and then consumed. So in that previous example, the N2O2, because we make it early, but then consume it later, that makes N2O2 an intermediate. That's what we call an intermediate. Formed and then consumed. Produced and then consumed. Now, elementary steps in what's called molecularity. The key thing, what's so important about these elementary steps is that they give us critical information about rate law of the overall reaction. Because you can consider each elementary step for having its own rate law, and here the coefficients do matter because this isn't an overall balanced equation. This is a single individual event that involves one molecule, two molecules, whatever you're writing. It's not the overall process. It's a single individual event. The coefficients do matter, and the coefficients actually do become the orders here because they're saying how many of these molecules are involved in this one single event. So we have unimolecular and elementary steps. Again, this idea of, we call this molecularity. A unimolecular step would be a reaction that involves just one single compound, and that's it, one molecule that possibly breaks down or turns into something else. That would be unimolecular. And a unimolecular elementary step, this would be first order because it only involves one molecule. And that's it. A bimolecular reaction. Now, this is a reaction that involves the collision of two molecules. So two molecules have to collide. Two molecules have to collide in a bimolecular step. This is not an overall process. This is an individual event. And because this involves the collision of two species, this is a second order process, right? Two things are contributing to this single event. Now, a termolecular step, as the pattern goes, this would involve the simultaneous collision of three species. Therefore, this would be third order. However, this is actually incredibly rare. It's very difficult to get three things to collide just the right way with just enough energy oriented with the correct positioning in order to get a successful reaction. So as we start to have sort of go beyond third order and start to involve, maybe four things, five things, six things, all colliding at the same time, the odds of that happening actually become quite small. Now, I'm going back to the previous slide here. So this is our previous slide. And just I want to point out the molecularity of these two elementary steps. Well, the first elementary step involves two molecules, so this would be bimolecular. The second elementary step also involves two molecules, so the second elementary step would also be bimolecular. But I could also write a rate law for this step, for step one, because this is not an overall process, this is an elementary step, and it would be rate equals K times the concentration of NO squared, because there are two NO molecules. So this step involves the collision of two NO molecules simultaneously. Now the rate law for the second step would be different because it involves different molecules. It would be rate equals K, and it would be the concentration of N2O2 raised to the first, because there's only one N2O2 molecule involved in that individual process, times the concentration of the O2 molecule also raised to the first, again, because there's just one of them. But here I do use the coefficients to turn into orders because it's not an overall process, it's an individual event. So I'm essentially describing the rate law of that individual event. Now, rate determining step, or something I'm going to abbreviate as RDS. A reaction is only as fast as its slowest step. This is very much like, you're only as strong as your weakest link. That's the idea. That a reaction is limited by, its overall rate is limited by its slowest step, meaning its slowest step essentially controls the overall rate of the entire process. The rate determining step, the slowest step, determines the rate law and the molecularity of the overall reaction. Putting this another way, and this is the big fat point about reaction mechanisms, the rate law of the slowest step, i.e. your rate determining step, is the rate law of the overall balanced chemical equation. And that's how we use reaction mechanisms to get rate law. We figure out the slow step, which oftentimes is actually going to be given to you in the problem, like you'll see the word slow next to it. And you want to take that step, write a rate law for it, boom, that is your overall rate law for the entire reaction. It's saying that, look, this is the slowest thing that's happening, so it doesn't matter the speeds of everything else because they're super quick in comparison. You are as fast as your slowest step. How to evaluate if a reaction mechanism is valid. There are two things that will tell you if a proposed reaction mechanism actually fits with a balanced chemical equation. And they're both equally important. So number one, you have to be able to add the individual steps together to get the balanced equation. That has to happen. If your steps do not combine to create the balanced chemical equation, then it's not a valid mechanism. But number two, the mechanism must agree with the experimentally determined rate law, meaning the rate law of the slow step of the mechanism must be the same as the rate law for the overall balanced equation. So those two things have to happen. The steps have to add together to create the balanced equation, and the rate law of the slow step has to be the same as the rate law of the overall balanced equation. So a simple problem with reaction mechanisms. So we have an overall reaction here, 2NO2 plus F2 yields 2NO2F, and it's asking what would be the rate law for the overall reaction. We have a proposed mechanism, And we have these series of steps. Now, first of all, let's just sort of check to make sure that the steps do indeed add to create the overall balanced equation. So let's see, keeping reactants as reactants, products as products. Well, the F will cancel out. Everything else won't, does not cancel out. So I'll combine the 2NO2 plus the F2 and then combine the 2NO2F. Okay, good. So the steps do indeed combine to create the overall balanced equation. Now you'll notice right here, this is actually very common in reaction mechanisms, telling you speeds of the individual steps. That it tells us that the first step is slow and the second step is fast. Well, by telling you that the first step is slow, that means that's the rate determining step. That's the slow step. So that means that the rate law of this step is the rate law of the overall balanced equation. So all we need to do is write a rate law for that first slow step. Now this first step is a bimolecular reaction, so we should expect to write a second order rate law, one that depends on NO2 once and F2 once, because that individual step simply involves the collisions of the two. So the rate law for the overall reaction is going to be that of the rate determining step. So it's going to be rate equals K times NO2 to the first, because there is only one of them in this process, times the concentration of F2 raised to the first, because there is only one of them in this process. Basically saying that, look, we depend on that slow step. That slow step simply involves the collision of one NO2 and one F2. So that's the overall rate law. What if the rate determining step has an intermediate in it? And this is actually how you can get into possibly having halves or fractions as orders, which is absolutely a thing. We're just not getting into it in this particular class. So as an example, we have a series of elementary steps shown here, step 1 and step 2. And step 2 is the slow step. So we could write a rate law that would be based on the slow step, right? We're just looking here. Rate equals K times the concentration of N2O2 raised to the first times the concentration of Br2 raised to the first. But when you examine this, right, N2O2 is produced in the first step and consumed in the second step. That makes N2O2 an intermediate. One of the first things we learned in this unit was that rate laws have to be in terms of reactants. You cannot have a rate law that's in terms of products, and you absolutely cannot have a rate law that's in terms of an intermediate. It can only be in terms of reactants, not intermediates and not products. So that means that we have to replace the N2O2. We're going to replace it with what made it. So if we examine the steps that are shown to us, what reactants produced the N2O2? The two NOs did. So two NOs had to combine in order to create the intermediate N2O2. Writing NO and NO sort of together, we get this sort of NO times the concentration of NO squared. So we're going to replace in our rate law, which is our intermediate here. That's bad. We don't want that. We're going to replace that with this. And we get the rate is equal to K times the concentration of NO squared times the concentration of Br2. So if you have an intermediate in your rate law, you have to look back at your previous steps and replace it with what made it. You can't leave an intermediate in the overall balanced equation. We also have other things that can pop up in a reaction mechanism. The other thing that we can label and identify in a reaction mechanism is a catalyst, which I know you've heard of before. And I know that you're going to tell me that it's something that lowers the activation energy of our reaction, and I completely agree. And it's something that speeds up a reaction without being consumed, and I completely agree with that. But how we wanted to define a catalyst in terms of reaction mechanisms, basically how are we going to recognize one in this particular setting, is through this definition. And it relates to this first part of a catalyst definition. And part of a catalyst's definition is that it is not consumed in the overall reaction. So what we want to look for is something in the reaction mechanism that is consumed early, meaning it got used up, but then in a later step, it got produced. So it was essentially regenerated. And if you look at this definition, this is truly the exact opposite of a reaction intermediate. A reaction intermediate is something that is produced early and then consumed later. A catalyst is going to be consumed early on, but then regenerated, produced later on in the reaction mechanism. Looking at reaction mechanisms in terms of activation energy, which is actually going to be related to the very next video. What a catalyst does in terms of the activation energy, by lowering it, what we have here is a Maxwell-Boltzmann distribution of collisions, effective collisions, basically things that will generate a reaction, right? Things that get us a reaction. And the reason why lowering the activation energy speeds up a reaction, here we have uncatalyzed versus catalyzed, and if we lower that activation energy, which is what we have in this second figure here, right, we simply move the activation energy further to the left, make it a lower value on the x-axis, i.e. make it here, again, which is what is shown here, and you see suddenly we have a whole lot more area under the curve, indicating that we have a lot more collisions that are going to be considered effective, meaning you have a lot more reaction now. So that's why lowering the activation energy speeds up the reaction, but by a catalyst. Now we're going to end with just two sample problems with our mechanisms, putting everything together. So we have a 4-step reaction mechanism. It really doesn't matter that it's 4 steps. You just kind of look at them all individually. And we have the overall balanced equation. And question 1, write the rate law for this reaction. Write the rate law for this reaction. We want to find the slow step. That's the rate determining step. And the rate law for the slow step is the rate law for the overall reaction. So step 1 is the slow step. That is a bimolecular reaction. It involves the collision of an HBr and an O2 molecule. So the rate law for that slow step is going to be rate equals K times the concentration of HBr times the concentration of O2. There are different K values basically for every individual step, saying that, the rate constant is different for every individual elementary step. And because I'm using step 1, I am going to use K1 there. List all intermediates in this reaction. So intermediates are produced and then consumed. So that's what we want to look for. We want to look for things that are made early and then used later, like HOOBR, Huber. Huber is made in step 1 and it is produced in step 2, so that absolutely makes it an intermediate. Also an intermediate produced early and then consumed later. Notice this 2HOBR. It's produced in step 2, and then one of them is used in step 3, and then the second is used in step 4. So we have 2 intermediates here, HOOBR and HOBR. And list all catalysts in this reaction. Well, now we want to look for something that is consumed early, but then produced. So we want to look for something that is used up, that's on the reactant side in an early step, but then it's on the product side in a later step. And if you examine this reaction mechanism, there is nothing that fits that description. There is nothing that is a reactant early on that is a product later on. HBr is a reactant always. H2O is a product always. Br2 is a product always. O2 is a reactant always. We don't have anything that is used up early and then regenerated later, so there are no catalysts. So be careful of that. That can absolutely be an answer. And then another question right here. Experimental rate law for the reaction between NO2 and CO to produce NO and CO2 is rate equals K times the concentration of NO2 squared. Reaction is believed to occur via these 2 steps. What is the equation for the overall reaction? Well, in order to do that, you want to add together your steps. Right, that's all we need to do. If we simply add together the steps, when we do that, NO2 will cancel out because it's the same on both sides, and NO3 will cancel out because it's the same on both sides. So we get, for the overall balanced equation, after canceling out the same stuff that's the same, is NO2 plus CO yields NO plus CO2. So I simply sum together the reaction mechanism steps to get the overall balanced equation. What's the intermediate? What's the catalyst? Okay, well, an intermediate is produced and then consumed. So looking at this, produced early, consumed later, NO3 fits that description, right? Because the NO3 is made in step 1 and then it's used up in step 2. So NO3 is our intermediate. Catalyst is consumed early and then generated later. So looking at that definition, something that is used up early and that we get back later, NO2 fits that description, right? Because we make it in step 1 and then we regenerate it in step 2. And then the big question, what can you say about the relative rates of step 1 and 2? Which one is fast, which one is slow? Now there's a tendency, or an incorrect tendency, for AP chemistry students to say, well, step 1 involves a catalyst that makes it fast. No. No. Catalysts speed up the overall chemical reaction. They really don't have simply looking at where they're present doesn't really necessarily tell you anything, and that's not a correct reason for picking that step as being the fast step. What you need to do is remember that the rate law of the overall balanced equation is the same as the rate law of the slow step. And that is how you want to comment about the relative rates of these two steps. It has absolutely nothing to do with which one has the catalyst and which one has the intermediate. That's not what it's about. You have to look at the rate law of the overall balanced equation. Now, the rate law of the overall balanced equation is rate equals K times the concentration of NO2 squared. That means that is also the rate law of the slowest step in the overall balanced equation. That rate law involves the collision of two NO2 molecules. I know it's the collision of two NO2 molecules because the order is 2. So it's indicating that there are two NO2 molecules there. And then I look at my individual steps. Oh, look, step 1 involves the collision of two NO2 molecules. That means that step 1 is the slow step and step 2 is the faster step. The rate law of the slowest step must be the same as the overall balanced equation, as the rate law of the overall balanced equation. So they gave us the rate law of the overall balanced equation, match that with an individual step, and then that's, you know that that step is going to be your slow step in the overall, the slowest step out of all the elementary steps.